All right, so 10.1 was all about the vocab of circles and then the couple of theorems that were attached to it. So this one just asks for the name that best describes the figure, because again, you might have more than one option. You want to do the most specific. So line CD is a line that touches the circle at 2 points, which would make it a secant. And then line AB would be a line that intersects the circle at exactly 1 point, which is a tangent. So a couple people put tangent and segment. Be careful. If AB was to be a segment, then you would see the line over it without the arrows. That would be the difference between a tangent and a tangent segment. Point of tangency would be the single point B.
Oh, okay.
Any other questions on that one? All right, number 2 said tell how many common tangent circles the tangent. How many common tangents the circles have? Okay, which should just be one. You can only make one tangent, whether it be a segment or a line, that hits both those circles at 1 point. Number 3 is AB tangent to circle C and explain. So in order for them to be tangent, or for that line AB to be tangent to the circle, it has to be perpendicular to the radius, which is that 16. So you had to show that this was a right triangle. So 16 squared plus 30 squared had to equal 34 squared. 30 squared would have been 900, 16, 256, and 34, 1,156. Add the 900 and the 256, and you get 1,156. So because those two were equal to each other, this is a right triangle, which makes that tangent. All right, and then the last one, there's like ice cream cone looking ones, right? So this is 2 tangent segments coming from outside the circle at the same point. So for these, you just set them equal to each other. 3x minus 1 would equal 2x plus 11. Subtract the x, add the 1, and x should have equaled 12. Questions on those? Okay, so let's go to homework. All right, so these are a little bit trickier. This is where your algebra skills come back into play. It says find the values of the variables, and exercises 24 to 20. Oh, we're not going to do those. 21. So we start with 21. So in order for this this line to be tangent to the circle, there has to be a right angle there, which means this is forming a right triangle. So if I were to use the Pythagorean theorem, it would say that this side, which is r squared, plus this side, 24 squared, should equal this whole side, which is r plus 16 squared. So for the ones on the left, obviously r squared stays r squared. 24 times 24 is 296. Thank you. Way off. 576. And then this, I have to expand and FOIL. So r squared plus 576 equals r squared plus 16r plus 16r plus 576. R squared plus 576. Oh, okay. Let me delete just part of it. Oh, because I did 24. Gotcha. Holy moly. 576 equals r squared plus 16r plus 16r plus 256. R squared plus 32r plus 256. Okay. So as soon as I get it to this point, hopefully there's like some connection with your algebra skills, right? First of all, you had to know that you can't just distribute this power. You have to expand that and FOIL it, okay, which is what we did. But then when I get to this point, I would group together my r squareds and my r's. So if I subtract the r squared, whether I do it from the left or the right, these are going to cancel. 576 equals 32r plus 256, and then I want to subtract the 256. 32r, 6, 320, divide by 32. and r is 10. So you have to, again, utilizing some algebra skills, that expanding and foiling, and then grouping together the r squareds. So the same thing is going to happen with 23. I would set it up the same way. This would be r squared plus 14 squared should equal r plus 7 squared. R squared, and this is 296, right? Yeah. R plus 7, r plus 7. R squared plus 7r plus 7r plus 49. When I subtract, well, let me combine my like terms first. R squared plus 2. Subtract the r squareds. They're going to cancel. 296, 14r plus 49. Okay, and then divide it. You can reduce it. You can divide it however you want. So that's divisible by 6. Nope, it's not. It would go in. Did I do that math right? 196. Thank you. Should stop being lazy and actually multiply it out. There we go. So 147 divided by 14. And then it would go in 0 times 70 would be that 0.5. So you can write it as 10 and a half. You can write it as 10.5. You could have, I would have been okay with you leaving it as 147 over 14 too. Usually when you're talking about a segment length, you would at least get it into mixed number or improper. Or decimal. Any other questions from the homework? So every section is going to pull back in a little bit of those algebra skills. You got to make sure that you stay on top of it, okay, so that should they show up on a quiz or a test, you're ready for it. All right, so we're going to go to 10.2. So 10.2 is arc measures. So we're going a little bit more vocab and then actually finding some of the measures of the arcs and angles in a circle. So we start with what a central angle is. So a little bit of vocab. A central angle is an angle whose vertex is the center of the circle. So any angle inside my circle in which the two sides would be the radii and the actual vertex would be on the center. It's called a central angle. So in the diagram that's there, angle ABC would be a central angle. If I added a point over here, angle ABD is also a central angle. And angle DBC is also a central angle. So the two sides are still vertex, are still radii, and the vertex is the center. Alejandro.
What if it was a 180?
It's still a central angle. So like if I drew in here DBE is still considered to be a central angle, as long as its vertex is at the center. So arc is actually the part of the circle. So if you picture it to be like the crust of the pie, the crust itself is considered to be the arc. Okay, an arc is a broken part of the circle. And there's 3 different kinds: a minor arc, a semicircle, and a major arc. A minor arc is less than half the circle, or less than 180 degrees. The semicircle is exactly half the circle, which would be that 180 that we just drew in that last example. And then a major arc is an arc that's greater than half the circle, or greater than 180 degrees. So minor less than half, semicircle equal half, and major greater than half. So in this diagram, if you're given that DC is the diameter, so a diameter is going to be a straight line that passes through the center. That's how you can identify it's a diameter unless it says it somewhere. Okay, like this. If DC is a diameter, then arc AC, so we're going from A to C, would be a minor arc. It's less than half the circle. Arc DAC goes in that order. So I go from D to A to C. And that's half the circle, which would be a semicircle. And then arc ADC, so now I'm going A to D to C around this way, would be a major arc. So pay attention to the order of the letters because it will tell you what you should be which way you should be going around your circle.
Like for semicircle, like for DAC, could you just say DC?
So usually, because you can't differentiate between that being the top semicircle or the bottom semicircle, while the measures will be the same, it could be referring to two different ones, you'll need the third letter. So the question is, could I just call this one DC? Okay, but technically this could also be DC. So you would involve a third letter either way. Whether if you were talking about the top half, you would do DAC, and if you were talking about the bottom half, there would probably be an extra point down there to talk about it. Good question, though. All right, so find the measure of the arc. The measure of the arc is equal to the measure of its central angle. So whatever the angle is on the inside is going to be the same as the arc that angle forms, okay? So arc AC, which goes from here to here, is formed by this angle, which is 50 degrees, which means arc AC is 50 degrees. The little m in front of that is asking for the actual measure of it. So that's how you know it should be numeric. And the little symbol over the letters is the symbol for arc. So you'll either see like the word written out, arc AC, or you'll see the little arc drawn like that. Alejandro.
And you measure the length of the arc by degrees?
So length of the arc is different from measure of the arc. Length would be if I took a piece of string, went around it, and then laid that string against like a ruler. That would be length of arc. We are finding measure of arc, and measure of the arc is the degrees. Eventually, we'll see length, but not yet. All right, so CAD would go from C, oops, I went the wrong way, from C to A to D. So what do we know about that measure? It's 180 degrees because it's a semicircle. And then the last one is ACD. So I'm going from A to C around to D. What do we know about this measure? Good. It's the 180. That's the half circle plus the 50, which is 230 degrees. Questions so far? You used it here, right? We used it on this one. We took the sum of those two adjacent arcs and added them together. That was the arc addition postulate. Okay, adjacent arcs. Think about adjacent are the words next. It means next to, right? Adjacent arcs are arcs that have exactly one point in common. So QR would be adjacent to RS. They both share R. They can't overlap, and there can't be something separated between them. So RQ is not adjacent to ST. They're too far apart, right? They're not next to each other. And I can't say that RS is adjacent to TR. They overlap. So adjacent is literally sharing just one point. They can't overlap, and there can be no separation. So in this case, what arcs are adjacent to TQ? TS would be adjacent, so those would be adjacent. TQ would be adjacent to QR. Okay, so those would be adjacent arcs. Questions so far? Okay, arc addition postulate. So if you go back a ways, you remember we had segment addition postulate, we had angle addition postulate, which said if I take whatever the object is to begin with the segment, and I break it down into its parts, I add those parts back together, I get the whole. Same exact thing applies to arc. Okay, so the arc addition postulate says the measure of an arc formed by two adjacent arcs is the sum of the measures of the two arcs. So in this case, arc ABC, which goes all the way around this way, is equal to the sum of AB and BC. So that is the arc addition postulate, which we've already used, like you guys actually used it. Congruent circles and arcs. So congruent circles, we talked about yesterday, would be circles with equal radii. Congruent arcs, and arcs that have the same measure. And the arcs of the same circle or congruent circles. All right, so I have 3 different circles here, okay? If you look at that first circle, I have 2 arcs with the same measure, right? I have, go back. I have arc AC, which would be congruent to arc EF. They both are in the same circle, and they have the same measure. If you look at the blue circle, so what links the pink circle and the blue circle? What do I know about those two? Ignoring the arcs. What measurement's on there that links those two? Ignoring the angled measurement. The actual radius, right, is the same, which means what's true about the pink circle and the blue circle? They're congruent circles. So I could also say that arc AC is congruent to arc LM. They are congruent circles with the same arc measurement. But then if I look at, and this is a little hard because it's yellow, okay? That's an N. If I look at now the yellow circle, I have the same measure on the arc, but what's different about my circle? Now the radius is different, which means that I can't link arc BN to any of the other arcs being congruent. Does that make sense? So you either have to do it within the same circle, or you have to do it within congruent circles. These would not be congruent. So even though the measure of the arc is the same, they are not congruent. The measure is the same, they're just not congruent arcs. And it kind of goes back to that idea of the arc length. If I took a piece of string and I went around the outside of the arcs for the blue and the pink ones, those strings would be the same length. But if I go to use that on the white circle, that string's obviously going to be longer, right? So they're not congruent. All right, so what are the names of 2 minor arcs? Evan. RA is one, which can also be called AR, same arc. Okay, what's the second one? Good, RC. Or CR, same thing, right? Okay, Alejandro.
Can you name them with 3 letters?
Typically, if there is a letter in there, if there was an extra letter in there, then you can. Typically, you don't need the 3rd letter for major arc, or for minor arc. But if there was a letter here, and I called that ABR, that's still the same arc. All right, so then 2 major arcs. Alexa. ARC is, ARC would be a semicircle, right? Because if this is my diameter, that's exactly half. But go one more letter. What would be past C? ARD. Okay. How about the other way? So ARD would be around this way. What about, go ahead. DCA. Yep, DCA would be a major arc. So would be ADR, right? Or ACR. Those would be the other way you can work those. So there's a couple different options for major arc. Okay, how about a semicircle? What are the semicircles? ARC and AD. Oh, no, I read it in the wrong way. ADC.
Doesn't matter like which way you write it, right?
No, I could have written CDA as long as the D's in the middle. So CDA or ADC would be the same arc, and then ARC or CRA would be fine. Okay, an acute central angle. So it looks like the easy, obvious ones, there's two central angles here. Does ROC look like it's more than half of that line? Yes, which would mean it's not acute, correct? Which means the other one would be AOR. Smaller than half that line, which implies acute. Okay, and then two congruent arcs. They have to have the same measure. I only know one type of measure, right? Which was what? The semicircle. So those are my two congruent arcs. ARC and ADC, or CDA and CRA. Those are the only ones I know anything about. So when you look at a circle and it doesn't give you any kind of angle measurement, the only one you can assume is if it's got a diameter, that's going to be 180. Other than that, you can't assume anything would be an exact measure. Does that make sense? Question so far? If it gives you measure, now you can go a little bit further. So whether it gives you the angle or the arc, you can use it for the other end, right? So if this is 30, then I know that this is 30. And if this is 50, then I know that this is 50. So whether they give you the measure of the arc or the measure of the angle, they are shared. So it says give the measure of each angle or arc. How do I find arc WX? Good. I already have the 30 and the 50. I know that this is my diameter. It's a straight line that passes through the circle. So I would do 180 minus the 30 and the 50. And I'd get 100 degrees. And again, measure of arc should be in degrees. Okay, WOT we just found was 50 degrees. Now we're talking about the angle, still in degrees. XYT, so X, Y, T. How do I find that? Good, 180 plus 30, which would be 210. And then the last one, angle, WOT. WOT, which is this full angle here, which is what? 180 degrees. I took, which one was that? This is X, Y, T, right? So this I know is a semicircle, which would be 180 degrees, and then add to it the adjacent arc, which is at 30 degrees. All right, questions overall on any of it? So a lot of new vocab and then a couple of things about the arc measures and that kind of stuff, but hopefully it's still not too bad. All right, I'm going to publish.